Yeah, welcome. Hope you're doing well. Now, the last time we were talking about periodic table, I told you what periodic table was, properties of the periodic table, their chemical characteristics, their properties, the utilization of power, and the rest. Before we get going, there's some few questions I would like us to treat so that we'll know how we have been doing and then know if we have really been reading hard. Jam is reading by the corner, so you just need to watch some things. But anyways, today I'll be taking you separating techniques. But let's just go through some stuff to keep. Let's just go back. Remember, I told you the assumptions of periodic table are known as periodicity or known as the law of periodic table, which tells you that their atomic number are a periodic function of the atomic numbers. Now, and I told you how the ionization energy works. I showed you this table. I told you that the period is divided into groups and period. The groups are the vertical columns, the period are the horizontal zero. That these periods are numbered from period 1 to period 7. And I also told you that from period 4 to period 7, here you have the transition elements, and you also have the lanthanides and the actinides. I told you why they are called transition elements. I said they're transition elements because they have partially filled d orbitals. Very simple. And I also gave you instances of the subshell, the energy level, and also how to be able to put them together in their subshell. Now, remember the last time I was trying to draw some stuff for you. I give you something like this. And I see this is the nucleus there. Now your electron is here. Now if you remember vividly, I gave you a good source as the atomic number increases, as the element increases. Now, the maximum number of this K is 2, having 2 electrons here. The maximum number of the L subshell is 8. This is 2, this is 2, sorry, this is 2, this is 2, that's 4, 6, and that's 8. Same thing goes for the M, the N. So the maximum number of the K, which is the first one here, is 2, which is K. The second one, which is L, is 8. And I also taught you that once you've been given an element, an example, I used oxygen very, very well the last time, 16. Now I told you that oxygen has 2, 8, and I told you that oxygen has 2, 8, and 6. 2, 8, and 6. Because 2 plus 8 is 10, 8 plus 6, 16. Now, and I told you how to fix it in an electronic configuration and this table like this. Now, let's go one more time with it. I said the first one, you have your nucleus inside. Now, you go, this is your K, as I told you. Now, having to, I told you the first has just 2 electrons inside. Then the next has a maximum of 8. 4, 6, 8. And it's remaining 6. Then you have that ionization energy are energy that are required to remove an electron to make it a negative ion. An example, now for it to become octet, for it to become stable. And that's why they call group 8 element a stable element. That's starting from helium, a very stable element. Why? Because they have an octet structure. Group 8 elements, they all have an octet structure, meaning they have just either 2 8s or they have 2 8 8. It's complete. Oxygen is not complete, so it requires 2 more to make it complete, and that's why oxygen undergoes ionization energy. It requires energy for it to add another electron to itself. Now, I gave another example the last time. I also gave about magnesium. Magnesium having an atomic number of 12. Magnesium having an atomic number of 12. This is your nucleus. Now, this is 1, 2 here. This is 2. This is 4. This is 6. And this is 8. This is making it 10. Then this is 1. This is 1. This is 2. So that's 12. Now, that implies that magnesium does have 2, 8, 2. Now, magnesium undergo what they call electron affinity, meaning energy that is needed to remove an electron. So now, for it to become stable, we need to remove this electron from this magnesium. So once this electron is out, Now this magnesium now will become +2. Remember when I was dealing with oxygen, when you add, it becomes -2. Once you are dealing with magnesium, we are removing it, so it's becoming a positive sign here, +2. This electron affinity, I said electron affinity energy needed to remove. I said additional energy required to add. Now, since we have done that before, let's just rush things up. Now, I also give you that once you have been given that, you should add these two together. Now, remember I told you that your group 1, your group 2, they are known as metals. Although group 1 are known as alkaline metals, group 2 are known as alkaline earth metals. Now, ranging from group 3 down, they are known as non-metals. Now, once you are reacting a metal, which is magnesium here, with a non-metal oxygen here, you discover that, remember in your physics, they talk of like charges they repel and like charges they actually attract. Now, the bond formed here is known as ionic bond. The bond formed here is known as ionic bond. Now, I told you that this one has 2, 8, 2. This has 2, 8, 6. Now, this one needs 2 more for it to become stable. This one needs to release 2 for it to become stable. So once you have that one, you discover that this 2 goes here to make this one stable, and then this one just remains like that. So that's their ionization energy increases across the period. I talked to you about the atomic radius. I also explained how the atomic radius works. I told you that this is a nucleus, and in your maths, they told you that atomic the radius is the distance from the center here, or half of a diameter. So now the distance from the nucleus to each electron is what we call the atomic radius. Now, the more the electron shell increase, remember I told you that your periodic here, the elements in your periodic table, they are similar. How? Because they increase as the valence shell increases. Meaning, if you are talking of group 3, it means every member of group 3 has a valence shell of 3. How? Sodium. Sodium is how many here? Sodium is 11. Now, this is your electron. This is 2. This is 2, 6, 8, this is 10, and then 1. Remember, sodium is in period 3. Now, the next one is magnesium. This is sodium, 11. My next one is magnesium. Now, the same thing. Magnesium does. This is 1, 2, this is 1, 2, this is 6, 8, 10, and the third one, this is 1, 2. Now, you discover that they both have 3 valence shells. 3 valence shells. Valence shells. Now, I then told you that elements in the same group have the same electron numbers, meaning that look at lithium having just 3. You have this 1, 2, and 1. This is lithium. It has just 1 at its atomos electron, having 1 electron at its atomos valence shell. Now look at sodium having 11 again. Then look at it here. It has 1 again, 1 valence electron. So that implies that elements in the same group have the same valence electron. Elements in the same period have the same valence shell. There are 2 different things. Valence shells are different from valence electrons. These are the electrons. These are the electrons. These are the shells. Okay. Now let's take a look at some questions here. Now I said, moving from left to right across the period, the general rise in the first ionization energy can be attributed to the words. Now, A is a decrease in nuclear charge, B is an increase in nuclear charge, C is a decrease in spinning effect, D is an increase in spinning effect. Now, remember I've told you that they increase across the period. So there's an electron. So as it's losing that electron, their nuclear charge is increasing across the period. So therefore, the answer here is B, meaning that they are increasing across the period. Now, the next one. Now, the next one here. They say how many unpaired nitrogen sublevels. Now, this is nitrogen. Nitrogen, look at it here. Having atomic number of 7. Now they're asking you how many unpaired electrons are there in nitrogen sublevels. I told you about the sublevels, the KMLL. I told you about the PDF sublevels also, or subshells. Now this is 7. They're asking for the unpaired electrons. Now this is 2 and 5. That is nitrogen. Now how will we be able to find the unpaired electrons? I told you about the 1s, 2s, 3p, and 1s. This is your 2s. And I told you before you pair, you draw them first. And then you now pair. I remember they are in opposite spin. So now this is 2. So it's remaining 5 more. And I told you about the p. P is divided into 3. This is 2p. Divided into 3. So you have 1, 1, 1. So this is 2, this is 4, 5, 6, 7. So there's no need for you to pair again. They are complete. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Now this is paired. This is paired. None of these are paired. So you have 1, 2, 3 unpaired in nitrogen. So therefore, the answer here is here. A. You have 3 unpaired sublevels in nitrogen atom. I explain again. I told you before you pair, you put them down for singly. These are one of the principles of pairing in periodic table. Now you first put them first, and you don't put it like this. Just one. Once you are done, before you now start pairing them. So this is paired, this is paired, these are unpaired. So you have 1, 2, 3 unpaired nitrogen sublevels, electron nitrogen sublevels. So that's the answer. Now, they say the stability of the noble gases is due to the fact that they, remember when I was talking of noble gases? Now, noble gases are also known as this group 8. They can be called noble gas, they can be called inert gas, they can be called rare gases. Now, this group 8, remember I was telling you that it's because of their octet structure. Anyway, let's look at the question. They say the stability of the noble gases is due to the fact that they have no electrons in their atomic shell. That's a lie. They have configuration, meaning they just have a complete. They don't require anything. They don't need to add. They don't need to remove. They have an octet electron configuration. Their noble gases is not just due to the fact. Their stability is not just due to the fact that they are in group 0. Many people rush to answer this. It's not just due to the fact that they are in group 0. Yes, they are in group 0 in the periodic table, but their stability. They're going to say, what maximum number of electrons in the L shell of an atom? What the maximum number of electrons in the L shell of an atom is what? Remember, is your L, the third is your M, then the fourth is your N. Now, I told you that you first just have a maximum of 2 electrons. The next one has a maximum of 8 electrons. So now the first one here is your K, the next one is your L. Now they're asking what the maximum of electrons in the L shell of an atom. So the answer here is P. You just have 8 maximum number of electrons in the L shell of an atom. Now the next question here says the elements in the same period, elements in the periodic table have the same what? Remember I told you that elements in the same period, they have the same valence electron or number of shells. And I told you that these are shells. You can call it valence shell, you can call it just electron shell. Electron shells. So they have the same number of shells. They have the same number of shells. Now let's continue. Now they ask, what type of bond exists between an element X with atomic number 12 and Y with atomic number 17? Now let's look at it. It's very, very critical. Now they said X atomic number 12, and Y atomic number 17. That's 12. 2, 8, 2. Now this is 17. So you arrange it with 2, 8, 7. I remember we dealt with nitrogen and non-metal. Remember this is a metal and this is non-metal. So that's what they're asking you. The bond between metal and non-metal, and I used magnesium and oxygen as an example. But I said the bond here is ionic bond. Now ionic bond is also known as electrovalent bond. When you have ionic bond or electrovalent bond. metallic properties of the element tend to increase across each period. Really, which of the following questions is correct about the periodic table? The non-metallic properties of the element tend to increase across each period. So they are telling here now that is it true that the non-metallic properties, starting from this place, they increase here. The valence electrons, the atomic number, it increases progressively across the period, and that's very, very true. They increase across the period. But let's look at the C and D. Why is C and D is not correct? They say elements in the same group have the same number of electron shells. Remember, I told you electron shells are different from valence electrons. Now, electron shells are these that I told you. Just these. These are the shells. And I told you elements in the same group have the same number of electron, valence electrons, and not electron shells. Now the next one say elements in the same pair have the same number of valence electrons. So now it's just the opposite. Elements in the same pair have the same number of electron shells, not valence electrons. Elements in the same group have the same number of valence electrons and not electron shells. Okay. I think that's for periodic table. So let's just go through separation techniques. Now, once you hear about separation techniques, so many things come to your mind. Separation techniques. Now, separation techniques are just the way we separate mixtures of different substances. Now, there are various types of separation techniques. We have sieving, we have decantation, we have fractional distillation, we have sublimation, we even have centrifugation. Now I'll just be discussing a little of them more. Now, once you hear about sieving, it separates solids of different sizes. Examples are chalk particles, or even the local term we use, Gary. We use sieving. In the process of making cassava flakes, which is commonly known as Gary, we use sieve to separate them because they are of different sizes. Now, once we talk of decantation, you just need either a cup or a test tube, something like this, and then it's just used to separate a solid that actually dissolves. An example, maybe you put let me say sand particles. Now these are sand particles inside water. Now how do you decant? You just pour it slowly into another cup or into another test tube, and then leaving behind that solid particles. So that is about decantation. Now once we talk of fractional distillation has to do with separation of miscible liquids. Sublimation, let me go to crystallization. Crystallization has to do with separation of mixtures that decompose easily on heating. Now that's the difference between this and evaporation to dryness. Now, unlike crystallization, evaporation to dryness cannot be used to separate salts that decompose easily. They are majorly used in separating salts. They are used in salt industries, where you can use a water bath where you separate the salts. An example is salts found in oceans and the rest, or seas. So they leave them to evaporate, leaving behind the salts. So the evaporator is very, very easy. Now, crystallization is mostly used in drug industries and also in the production of sugar because they decompose easily. Now, sublimation has to do with the separation of solid and sublime. Now, when you hear sublimation, it means the changing of a solid particle to a gaseous form. Solid to gas, that's what you mean about sublime, meaning the solid is able to sublime. And example is iodine. Iodine is able to sublime, is able to change directly from solid. You don't need to pass through from solid to liquid. It changes directly from solid straight to gas. Now, centrifugation, it just has to do with separation of two different solutions An example, let me see a blood sample and plasma plasma. Now these two, they cannot mix well. So what they do, they use a machine known as a centrifuge. Now they place them at different position, and then they are allowed to spin. Now once they start spinning around, if the plasma is here, it begins to dissolve. It spins till all the whole plasma now dissolves at the bottom. Normally they use either a solvent, let me see water, so that because it's like a beam balance, in order to neutralize this one here. So the weight here is different from the weight here, so they just fix it here and then they allow it to spin. And then every solid particle at the top, it increases. It I think it increases now. It goes down. It goes down, and then once you say Fourier method, separating Fourier method, Fourier method. Now, this one is quite easy. Just like using your filter paper, something like this, and then you just put something like this. Now, it's used to separate solid particles from a solution. Example is when you put chalk particles inside water, and this is your cup, and there are chalk particles inside the water. So you have to separate that particle from there. You begin to pour it inside your sieve, and then that chalk particles remains at the top. I have separated them. Now, another separation technique that I would also like to treat is what we call fractional distillation, using separating immiscible liquid. That's where you now talk of how your crude oil are being formed and the rest. Anyway, let us go straight to the questions and then we'll begin to see more about how the separation technique works. They say you obtain pure water from a mixture of sand, water, and metanoic acid. Now, let us draw something. Now, this is your bucket, and now there's a mixture of sand. Remember, there is water inside, and then there's metanoic again. So now, which method? Now they said fractional distillation. I told you fractional distillation has to do with immiscible liquid. Now, water is a solvent here. Metanoic acid is different. Is a solution. Now, they can actually mix. So this is out of the complex. Now they say filtration followed by distillation. Once you are doing filtration, you talk of solid particles that float on top. Now sand dissolves in water, so you cannot use filtration followed by distillation. So that's wrong. And the next section, really. Now many people rush to this. Why? Because you see, once you add sodium hydroxide, of this acid, be able to neutralize the acid. Okay, that's not actually true. That's very wrong. Very wrong. And the next one still says neutralize with sodium hydroxide followed by distillation. Neutralize with sodium hydroxide followed by filtration. I think I'll actually go with this because once you neutralize with sodium hydroxide, you're able to remove this. So you're now left with your sand and your water. Now you can now filter it using your filter paper. You can now filter using your filter paper. The sand there now will remain at the top. So I'll go for this. Now the next one said fractional distillation is used to separate starch. It says an insoluble substance from a soluble volatile substance. A substance which are absorbed differently and which define their solubilities in the solvent. Liquids with different boiling points. Remember I told you that fractional distillation has to do with immiscible liquids, and I told you of crude oil. That crude oil uses fractional distillation. There are so many ways, so many different products that are being removed from during fractional distillation. So now once you're doing fractional distillation, you don't look at insoluble substance or insoluble volatile. So this is wrong. That is a substance which are absorbed differently and which define their solubility in solvents. This is wrong. Now, liquid will differ in boiling points. Now, once you talk of liquid will differ in boiling point, you will begin to notice that immiscible liquids have different boiling point, and that's why they can't mix. They have different boiling point, and that's why once you begin to separate a hydrocarbon, you can get crude oil, you can get kerosene, you can get different liquids there. And so I'll go for this liquid with different boiling points. It's not just a regular gas, liquid, or solid varieties for a mixture. Now, let's go to the next question.
Now they said a mixture of oil. Okay, I think this is supposed to be a mixture of oil and water. Mixture of oil and water. Now, imagine this. Remember that oil and water cannot mix. Oil is actually insoluble in water. So now this is your water, and then your oil is just on top. Now this is more like saying separating an insoluble substance from a solvent, because water is a solvent. So a mixture of oil can be separated and water can be separated, and water can be separated easily by what? Now this is sublimation. Remember I told you that sublimation has to do with changing directly from solid to gas. Nothing concerns solid yet, so this is out of the context. They say evaporation to dryness. And I told you, using evaporation to dryness, we are talking of separating salts. So this is out of the context. Now they say using separating phoneme method. Using separating phoneme method, and I told you how the separating phoneme method works. It's like this: it has you use a filter paper, then you're able to just pour it down, and then you able to filter. So your answer here is using a separating phoneme method. Then the next question says, sieving is a technique used to separate mixtures used to separate mixtures containing solid particles of small sizes, large sizes, same sizes, different sizes. Remember vividly I said sieving is used in separating mixtures of different sizes. So don't rush and then go here and then say small sizes. That's very, very wrong. That's very, very wrong. Now they say sugar is separated from impurities by A distillation, B evaporation, C precipitation, D crystallization. Remember I explained crystallization. I say crystallization is mainly used in drug industries. And not just drug industries, also a sugar industry. So there is to separate sugar from impurities. Now there are other stuff that I would like us to look about these impurities and how they do their stuff. Now let's look at chromatography. And chromatography uses separates a solute from a solution. This is chromatography. It separates solutes from solutes from a solution. When you talk of solute, you talk of particles that can dissolve in a solution. When you talk of insoluble solutes, you talk of particles that cannot dissolve in a solution. When you talk of solvents, when you talk of solvents, it refers to things that dissolve other mixtures, e.g. water. Another when I think of mixture of oil and water here, water sounds like the solvent here. Oil is just is an insoluble solute. It's insoluble. It's insoluble. So it cannot actually dissolve inside. Now there's another one I actually forgot to say, magnetic separation. Magnetic separation. Now this one just separates magnets from non-magnets. This is separating magnets from non-magnets. Magnets from non-magnets. So that's why you see once you're trying to separate magnets, separate them, either you use a magnetic tool where you pick ions that magnets, and then once you have sand particles, and then you have some feelings of ion particles. Discover that once you use your magnetic tool, it will be able to attract this ion to therefore separating this ion from this sand. Separating the ion from this sand. Now we are going to be looking forward at majorly precipitation. Now there are some stuff I would like us to just look at carefully. There's some stuff I would like us to look at carefully so that we'll be able to use it to know when and what to separate and how to separate them. Now, I say sieving is used to separate solids of different sizes. Now, magnet separation, I say from magnets from non-magnets, decantation, insoluble solid from liquid. Where I explained if you have stone here, you can just decant. can just decant it. Then I now talk of distillation where you remove solvents from a solution. So you remove solvent from a solution. Then I now talk of chromatography solely from a solution. I talk of centrifugation where you have to use a centrifuge machine to separate the two of them. And I talk of filtration where you use your filter paper to separate them. Now, this filtration, you can use them in the purification of water. Filtration can be used in the purification of water. Purification, purification of water. And this is just a chemical formula capable of subliming. I told you iodine. I told you iodine. Sublimation. An example, I said iodine. You want to use iodine. You are able to separate iodine and even ammonium chloride. This is ammonium chloride, NH4, Cl2. This is ammonium chloride. Now, you see that the iodine can undergo sublimation, ammonium chloride. Why? Because they can change directly from a solid to gas when heated. Now, they don't need to just pass through solid, liquid, and gas. They don't need it. They don't need it. They just go directly. So you don't need this. Now, I also talked of fractional crystallization used to separate solid solid which are present in the same solution. So once you have a solid solute in the same solution, in the same solution, in the same solution, once you begin to have solid solid in the same solution, that's when you now begin to look at their temperature. Then how to separate them, you begin to look at their temperature, and then you have to allow them to cool at a particular temperature before you're able to separate them. Now, remember this is different to fractional crystallization has to do with if you look at their temperature, that's fractional crystallization. So you don't get me wrong. Fractional crystallization. Now, we want to talk of fractional distillation. Fractional distillation. Distillation. Looking at their boiling point. This is boiling point. This is boiling point. Now, I also talked of, okay, I didn't actually mention precipitation to separate soluble solid from a solution. An example, still the same thing, it works the same way as decantation. Decantation and precipitation. They do the same function, they sell a solution. So decantation and precipitation actually do the same work. They separate soluble solids from a solution. Now, we did also mention about, okay, I actually mentioned about crystallization, where actually they are used in separating, making sugar and also drugs. Now, an example is copper 2 tetrasulfate 6. Now, once we talk of copper 2, these are actually write your chemical formula. Copper 2 tetrasulfate 6 pentahydrate. This is an example of one that undergo crystallization. Copper 2 tetrasulfate 6. Use it to separate. You can use it to separate this salts from impurities. Very easy. Now, I also told you I didn't actually talk more on the chromatography, but this chromatography, their own way actually different because they separate solutes from a solution, and all of them have their own different method. They have different method of separation. Different method of separation. Now, chromatography uses a solvent moving over a porous adsorbent medium. Now, chromatography are divided into different forms. You can have paper chromatography, you can have the TLC, or you can even use gel to separate. So they have different methods of separating. And there's what we call purification of substance or test for impurity. And impure substance is a mixture. So once we talk of an impure substance, now when is the substance said to be impure? Now, an impure substance is a substance that has a mixture that has a mixture. So that's an impure substance. Pure substance has a mixture, and definitely though, once they have that mixture, they will have different particles and different method of separation. Different methods of separation. Okay, before we go, let us take a quick look at some things here. Okay, I didn't mention flotation. Flotation. Flo- Flotation. Now, so the many metallic ores are found in nature in low concentration. So these are usually sulfide mixed with earthly materials before the metal is in ore and then an iron ore. So flotation here just has to do with lowering or increasing the concentration of the impurity. An example is iron. Iron has many impurities. So you have to separate impurity like to form an ore, which is bauxite. Let's talk more of the bauxite. Now, in separating a mixture of bauxite, you have to go through flotation, meaning you have to increase the concentration of this, and then before you can actually separate the impurities from this bauxite. You have to get a pure ore of iron. You have to get a very pure ore of iron. Now, let's go through other methods. Now, I didn't actually talk more on mixtures and how mixtures actually do their stuff. Now, there's what we call physical change and there's what we call chemical changes. Physical change and chemical changes. And physical changes are one which are easily reversed and no new substances are formed. Now, I said physical change, new substances are not formed. They are not formed. Now, chemical change. Chemical change. It's not easily reversed. Easily reversed. And new substances are formed. New substances are formed. And new substances are formed. Now, there are so many examples of both these physical and chemical changes. So many examples. Now, an example of a chemical change is burning of firewood. Now you have firewood and then it undergoes heating. And what you produce here is ashes. Now look very carefully. I told you that it's not easily reversed in chemical change. So there's no way you can reverse this ash back to firewood. But now a new substance is formed. Once you burn this firewood, you get an ash. So this is a new substance. This is a new substance. Now an example of physical change. Let me take for instance water. Once you have an ice, this is just a solid form of water. Now you have an ice and then you have water. And remember I said physical change, they are easily reversed. How? Once you put this under a low temperature of them is like 4 degrees centigrade. Now this water can reverse. So they are actually reversible. You can reverse from ice to water, water back to ice. There's no substance formed here. In chemical change, if firewood is being heated, it changes to a new substance known as ashes. Now the ash cannot go back to form a firewood. So this is one of the major differences between physical change and chemical change. One, physical change can be reversed. That is one difference. It can be reversed. Chemical change cannot be easily reversed. Physical change, new substances are not formed. Chemical changes, new substances are formed. An example again, I said ice changing to water and reverse back to ice. Chemical change, I said firewood changing to ashes, and ashes cannot change back
to firewood. Now, remember earlier I was talking of mixture. Remember I'm going back to physical change because once you talk of physical change, talk of chemical change, you still talk about mixtures. And I think your mixtures are mostly impure. Why? Because they contain several substances. And I think separation techniques are those techniques you use to separate mixtures of different substances. Mixtures of different substances. Now, once we talk of mixtures, we begin to talk of which type of element actually undergo mixture. Is air a mixture? Is soil a mixture? So let me list out some mixtures. Air is a mixture, soil is a mixture, even your urine is a mixture. Now, air is just a mixture of oxygen, carbon dioxide, nitrogen, rare gas. I want to talk of rare gas, you talk of the noble gases. You can put helium, you can put anyone, any of those noble gases. Now, they said dust. You have dust, you have moisture. You have dust, you have moisture. Now, when you talk of soil, you need to remember we have sand, we have clay, we have loamy, and the rest of them. Now, once you talk of urine, talk of the urea inside the urine, talk of water, because the urine actually contains water, it contains mineral salts, and that is why your urine tastes salty, contains mineral salts, contains urine. Now, these are some constituents of mixtures. Now, so many people actually mix mixtures with compounds. They don't know the difference between mixtures and compound. Now, these two are very, very different constituents. They are different constituents. Now, remember I told you that mixtures are just contains two or more constituents which can be easily separated by physical methods. Now, compound on the other hand are not cannot just be separated by, and like this one that sometimes which contain two or more elements chemically combined together. Mixtures can just be there and they are not combined chemically together and they can be separated by physical methods. But when you talk of compound, they cannot just be separated by physical methods. You cannot separate a compound using all these techniques of separation. You cannot. You can't use sublimation to separate a compound. No, because they are chemically combined together. So the major difference between mixtures and then compounds. Compounds. Mixtures, compounds. Now, they say the constituents are not chemically bound together, and exactly what I was saying. They say mixtures are not chemically bound together, compounds are chemically bound together. So you see elements here or substance, or let's use the word substance. I think that is more acceptable. Substance are chemically bound together. They are chemically bound together. Now, another difference here is that your mixture here may be homogeneous or heterogeneous. Why this one is always homogeneous? Why? Because they are always the same. Meaning you can have the same compound, but here substances joined together with compound. Now, they say the constant can be added together in any ratio by mass. A mixture cannot be presented by a chemical formula. A mixture does not have a chemical formula. Has no chemical formula. No chemical formula. A mixture has no chemical formula. A compound has a chemical formula. Now, once you talk of chemical formula, talk of formula that you can use to represent a compound. Example, you have water. Water. Now, if you talk of mixture, water is water. There is no chemical formula for water in mixture. But in compound, this is actually a chemical formula. Why? It has to do with two different elements.
chemically combined together. Two different elements chemically combined together to form this water. So that is another major difference between mixture and compound. So it shouldn't be that we begin to wonder how are compounds the same thing as mixtures, or are mixtures the same thing as compound, or what is actually their difference, or what's the difference between compounds and mixtures. Now there are also some stuff I would like us to look at about compounds and how you write their formula. An example is sand. I remember when I was writing some constituent of mixtures, I mentioned sand, I was writing all what sounds inside sand. Now the difference here now is that here, if you have sand here, remember I was telling you of clay, there's humus here also. But once you now become, if you start talking of compound, you talk of silicon. Silicon is presented as Si actually. Let me write it here for silicon, you talk of oxygen. And you see the difference there. See the way they are all different. So that's why I say this has to do with joining of two substances chemically. This one does not have to do with chemical bonding. This one can just be separated with physical method. You just can't use any physical method to separate a compound. You can use physical method to separate a mixture, but not a compound. Remember, you talk of water. Remember, I told you once you start talking of you talk of air here, we need to talk of oxygen, carbon dioxide, and the rest. But if you now begin to look at the other composition of compound, you now look at water having hydrogen and oxygen. Air is having oxygen and this. Air cannot be classified as a compound. They may just give me classify a compound. Why? Because it does not have two substances chemically combined together. Water can be classified as a compound and not a mixture. Okay, let's go through some other steps here. Okay, now let us assume that they ask you a question: how do you separate the following? And then they now give you a compound. Now, let's just use these simple terms here. They give you a compound, let me see, can just be separated by physical method. Now, the first thing for you to know is that remember I said mixtures does not have a chemical formula. Compound have a chemical formula. So if they give you, we begin to list out begin to list out separation techniques for you. You have to separate H to SO4, and there's a none of the above. Just go for the none of them. Why? Because you cannot use a physical method like this to separate a major compound like acid. That is one of the major differences between compounds and mixtures. Okay, let me just touch small areas of some separation techniques that in order to recapture our mind back. So we will not forget because the next time I come, we will not be thinking majorly on how these processes work, how they actually behave. So now I'm just going to list out some things for you, and then you'll be able to just use. I'll just list out some things for you to just use. This is sieving. So you have solids of different. You have sublimation. You have sublimation. So it's used to separate solids with sublime. And I told you the meaning of sublime. Solids which sublime. Remember I told you decantation, precipitation. All this, all of them are all used to separate insoluble solid. Insoluble solid from a liquid. I told you when you talk of insoluble solid, talk of solid particles that cannot dissolve inside the liquid. Now, Decantation, precipitation, filtration, and centrifugation all are used to separate soluble solid from a liquid. I told you that centrifugation has to do with using a machine known as a centrifuge. Then you put them into two different test tubes and then you spin until that insoluble solid dissolves inside the liquid. And then once you do that, you can be able to decant it or you can be able to filter. Now, evaporation to dryness, evaporation to dryness, crystallization, 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 and okay, and functional crystallization. All these ones are used in separating soluble solid from the solution. Soluble solid, and we want to use it to separate. Remember, actually, this is used to separate salts that do not decompose easily on heating. But it is all that separation of soluble solid from a solution. And when you talk of distillation, now distillation has to do with solvent from each solution. This is solvent from its solution. And once you deal with separating funnel method. This is used to separate immiscible liquids that cannot be mixed together. Immiscible liquids. Used to separating funnel to do that. And then remember when I was actually question of oil and water, two of them cannot mix, and that's why I said it's better work to use separating funnel method. And then the next one, we have chromatography. And then we have different forms of chromatography. We have gas chromatography. Okay, so chromatography is to separate the solids from a solution. The solids from a solution. This is separate the solids from a solution. Okay, I actually forgot about magnetic separation. When we talk of magnetic separation, we talk of separating magnets from non-magnets. Magnets from non-magnets. Okay. Now, let's take a look at it again. I said sieving solids of different sizes, sublimation solids with sublime from other solids actually. From other solids. Then now say decantation, precipitation, filtration, centrifugation. Okay, actually I think it's more better if I use decantation here. You know whether I use decantation here, filtration, and centrifugation. But this one I'm usually using separating insoluble solids from liquid. The evaporation to dryness, crystallization, fractional crystallization, precipitation falls here. Because precipitation also has to do with the solid that actually dissolves. So all these ones they are used to separate soluble solid from the solution. So the reason why I'm giving you all this breakdown here, so that once you're given a question, you begin to look at those mixtures and what is being mixed inside. Once you see different sizes, your mind should come across sieving. Once you begin to say, remember I had to give you an example, iodine under sublimation. I told you of ammonium chloride. And then once you see iodine, ammonium chloride, the separation from any other solid, just go that sublimation. Reason iodine can sublime, amino chloride and sublime. Now, decantation, filtration, centrifugation, insoluble solid from a liquid. I told you how decantation is. It's just our natural, the way we do things. Once you have your chalk particles, or you have, let me say, dust particles in your water, and you don't want to filter them off, you just decant. Meaning you pour the dirt or the particles gently down, until you are left with what you just want inside. The same thing goes for the centrifugation I told you about, using a centrifuge. And then I said, once you are using this machine, you want to get another solvent or something else, so you want to counterbalance the weight of what you are separating. And then there's a spin. It's the machine here spins it round till everything that is at the top dissolves down. Every particle that cannot dissolve, every insoluble solid, until it goes down, and the salt. And I said, salts that do not decompose easily. Salt that does not decompose easily. Now, crystallization is used in separating salts and sugar. And that's why they use it mostly in the production of sugar. They use this mostly in the production of sugar. Now, fractional crystallization also used in separating soluble solids from the solution. Now, from this point here to this point, they are all used to separate soluble solids from the solution. And that's why I said, once you just see question, it has to do a solid that is soluble in the solution. Look out for these options. Just look out for this option. And once you begin to see solvent from this solution, I told you solvents, water is a solvent. So once you see a mixture of water and any other solution, you should just rush to distillation. Your mind should go to distillation. Once you see solvent and just separating from rather. Now solvents from each solution. Now separating from I say immiscible liquid. You cannot mix water and oil. It's an example of immiscible liquid. Water and kerosene is another example of immiscible liquid. Why? Because of float at the top. Water and fuel or crude oil is an example of immiscible liquids. So they can always use, but you can be able to separate it using a chromatography. And actually, there are different forms of chromatography. We have a gas chromatography. These are the major constituents of the separation techniques. Okay. Okay. So now, if you actually have any question, you can actually just forward your questions to the website and then be able to go through it one by one in our next class. Okay, let me just touch a little bit, on something that actually came across in my mind. Wow, how does this thing actually go? How does it actually react? I came across it and I was just tempted to just come and just give a highlight on it, because I discovered that so many people don't know how to actually find it. How do you find equivalency? How do you get to know that this is status of a 6? I actually saw it coming up. How do you know that this is status of a 6? How do you know that this is a carbon 4 and the rest? So let me just give a little touch on how to be able to know all those ones. Now, imagine they give you a question like this. Let me start with it. Smaller one. Now, they now ask you how many viral electrons are carbon here in this compound. And this is very easy. Now, the carbon here is what you're looking for, so that stands as your X. So this is plus into bracket 2. Remember I told you that oxygen always has this radical over 0. So now this becomes X plus bracket 2 times you get minus 4 equals 0. This is your X This comes out because x minus 4 equals 0, so x is equal to 4. So you begin to, that's why I call this is carbon 4 oxide. Now, imagine they now give you a higher compound. Let me say they give you K2, Cr2, number of electrons or valency in potassium this compound. Now, the potassium becomes 2x. Why? Because it has 2 here. It becomes plus, this is 2, then plus into bracket, this is 7 times minus 2. Remember, I said this always has minus 2 here. Now, this is your 2x plus 2. 7 times x, this is plus minus 14, all equals 0. So this is your 2x plus this comes out plus 2 minus 14. This equals 0. So now, this is 2x, 2 minus 14 will give you minus 12 equals 0. So 2x equals 12. Why? Because close the eyes and it changes the sign. And divide both sides by 2 over 2. So this is 6. So now, to name this compound now, you now be having this is actually potassium with 6 Pi, and this is 7, so you have, or you say heptaoxide. Any of them can go. So then can be 6 heptaoxide. So this is one of the ways you have to, if you want to name your compound, and you want to know whether it's 6, if it is 5, if it is 4 you have to use, is it 3 you have to use, is it 2 you have to use. This is how you actually do it. Now let me give you a clue. Now this carbon 4 oxide, I also known as carbon dioxide. Why? Because of these two. Because of these two. These two. So is either carbon dioxide or carbon 4. But so many people don't even know the difference. Many people call carbon dioxide CO, which is very, very, very wrong. Carbon dioxide is not CO. They are two different things. This is carbon monoxide. This is carbon monoxide. Why? Because it has just one oxygen. So when you talk of one, you call it mono. Once it's two, you call it dioxide. It's either you call it carbon dioxide or you use the way I've calculated the carbon here. Then I have carbon 4 oxide. Okay? Just in case you just see it in your your question, you should be able to use it and then get what you are looking for. Alright, let's see some importance of chemical equations. Although we didn't actually prepare for this, but I just want to give a highlight of what we'll do the next time we see, so that we will not be new to it, so that we want to prepare ourselves for it. Let's give a highlight of some chemical equations and then how to balance chemical equations. Now, there are so many laws of chemical equations that we actually feel them. Chemical equations. Chemical equations. There are so many laws of chemical equations. Now, imagine they now give you sodium plus chlorine. It's a balanced equation. They give you, let me see, sodium hydroxide plus an acid. Balanced equation. Now, very, very easy. This one is just easy. This one is direct. Just add them together. Sodium chloride. Now, balancing this, pick the first and the next. You have sodium chloride plus pick the next this. You now be having H2O. So that means you have two atoms of hydrogen. So you need to calculate once you are balancing the equation, the number of elements at your left hand should be equal to the same number of elements at your right hand. Why? You have one atom of sodium here, one atom of sodium here, one atom of oxygen here, one atom of oxygen. You have two atoms of hydrogen. That's why you have two atoms of hydrogen, H2 here, H2. You have one atom of fluorine, you have one atom. So this is a balanced equation. This is a balanced equation. Now, what if we are now given sodium hydroxide plus H2SO4, SO4. We now have to balance this. Sodium hydroxide plus H2SO4. Now, you now begin to wonder how am I going to actually balance this? Now, look at the way I actually pick this. Pick this. So you're going to still do the same thing. Still going to do the same thing. So now you have very good. You now put this plus water. Now you can't just write this like this. You can't just write this like this. But this it can also be permitted, but you just can't write it like that. But let's just see how it's going to go. Now this NA, you've written it, you followed the step I said, pick NA here, OH here. Now let's check. Sodium is 1, sodium is 1. Good. How many oxygen do we have here? We have 1, this is 4 plus 1, 5 oxygen. Okay, we have 4 plus 1, 5 oxygen. Very, very good. We have 1, 2, 3, we have 3 hydrogen. We have just 2 hydrogen here. This is an unbalanced equation. Unbalanced equation. Why? Because the number of hydrogen here is not equal to the number of hydrogen here. So you begin to balance it. Now, how do you balance this kind of equation? Very, very easy. Now, once you add 2 here, now it changes the equation. Now you have 2 sodium attached here, meaning the oxygen has 2, the hydrogen has 2. These 2 affect everything here. The sodium is 2, the oxygen is 2, the hydrogen is 2. So you can only just put the 2 here. Okay. The sodium is now 2. The oxygen has changed from being 5 to now being 6 because this is now having 2 plus 4, so it's 6. The oxygen is still having 4, so 4 is 1. The oxygen is now 6, your hydrogen is now 4. So this is now a balanced equation. This is now a balanced equation. Very, very easy. Very, very simple. Very, very easy and very, very simple to balance a chemical equation. So there are some laws and there are some hidden things that you ought to know. How do we balance a chemical equation? Or what are the rules in balancing a chemical equation? And also what are the importance of actually balancing a chemical equation? Now I don't need to just list them, just few of them, how we balance chemical equation, their importance of. Because if you just give a chemical equation, they'll ask you what is the importance of this chemical equation. Now, once you have this, or you have just this and this, then they ask what is the importance of this. And the major importance is telling you the 2 elements are being combined. And it also tells you what is being formed. That is just one of the major importance of chemical equation. This plus this gives you water. It tells you, chemical equation tells you that, okay, for you to get water, you have to mix hydrogen, 2 moles of hydrogen with an atom of oxygen to get water. You have to get sodium chloride, which is a salt, which you call table salt. You have to mix one atom of sodium with 1 atom of chlorine, so you get sodium chloride. So this is an importance. See, it tells us the reactants Now, these two things are known as reactants. The reactant. What is formed at the end is what we call the product. So it tells us the reactants and the product. And the product. So the reactants and the products involved in the reaction. Involved in the reaction. Involved in the reaction. Another important is that it tells us individual elements and radicals involved. Like what I was saying, it tells you the individual elements involved. So I think what it tells us the reactants that sodium and chloride or chlorine, they are the reactants, and once they react, they form a product which is known as sodium chloride. And then they say the second importance is that it tells you the individual elements and radicals involved. Then I say it gives us a mental picture of the movement of the element radicals during reactions. It tells us how they move. An example, when I was giving you, I said you have a sodium hydroxide plus I said HCl. So now another important is that it tells you how they move. Remember I told you this moves and then joins to this. The reaction. How they move to be the reaction. Now there are some important messages that this tells us. We may just give you a reaction, then we'll not tell you what does this reaction mean. Now telling you that what does this reaction mean is different from what is the importance of this reaction. They'll tell you what does this reaction mean, and then there are some things that a chemical equation does not actually give out. When you have sodium plus chlorine, it does not tell you the speed at which these two things mix up. Just tell you straight the reactant, the product. This element plus this element gives you this. This has to move to this in order to get a product. And they don't also tell you the colors of the reactant and the product. Chemical equations don't tell you the product of any of the reactions. Okay, let's go through some examples of chemical equations and then we'll see how we need to balance them. How we need to see how since we really know how they are important. So let's go through some and then we'll see how we need to balance the equation. Now you have this. This is ammonia plus oxygen. Let's balance this equation. Now we have to balance the equation. Now you look at it, ammonia, oxygen. So now if you're balancing this equation, you now be having NO. Now what's water? Okay. Remember since we just have it, just pick one. Now look at it carefully. The equation is not balanced. Why? You have one atom of nitrogen, one atom of water. You have three tons of hydrogen, you just have two here. So your equation is not actually balanced. How do you now balance it? How do you now balance your equation? So now let's just click and see how we balance this. Now, let us read for a. Now I've changed the reaction. Now you have 4 number of nitrogen. Now this is 4 times 3, so this is 12 number of hydrogen. Sorry, the oxygen is still 2. Okay, oxygen is still 2. So now you have to complete it here. You then put 6. You now put 4. And we are going somewhere. Just how to balance a chemical equation. I said to balance a chemical equation, you must make sure that the number of elements at your right hand is the same thing as the number of elements at your left hand. So now we have 4 nitrogen, we have 4 nitrogen. We have 12 hydrogen, we have 12 hydrogen. but something is still missing. The oxygen is no longer 2. Now you have 4 oxygen here, you have 6 oxygen, making a total of 10 oxygen. Now this is very, very simple. Just go. This is 5. 5 times 2 is 10. So your oxygen is 10 here. Your hydrogen is 12. Your nitrogen is 4. Your nitrogen is 4. The oxygen here is now 10. Hydrogen is 12. This is a balanced equation. This is a balanced equation. This is a balanced equation. You have equal number of elements and compounds at the left hand. Equal number of the number of elements at the left hand, same number of elements at your right hand. So this is a complete and a balanced equation. Now let's look at another example of a balance. Okay, give you copper. Give you copper Cu plus hydrogen chloride. Then you're being asked to balance the equation between the copper and the hydrogen chloride. Okay, now remember how I always say this goes first. So you have your copper and chloride plus your hydrogen. You can't leave it like this because there's no compound like this without this. You can only hydrogen without writing it together because it's a gas. So you have to put it 2 here. Now to balance it, you put your 2 here. You have to put your 2 here. Now your hydrogen is 2, your chlorine is 2, your chlorine is still 1. So you just put your 2 here. And this is the balance equation. Balance equation. Don't ever go with Cu2, Cl2. This is very, very wrong. Very, very, very wrong. It's not like Cu2, Cl2. What you have is Cu, Cl2. Cu, Cl2. So this is a balance equation. You have 1 copper, 2 hydrogen molecules, 2 hydrogen molecules, 2 chlorine here, you have 2 chlorine here. So this is another balanced equation. That's another balanced equation. Okay, let me see, check if we have more balanced equation. Okay. Okay, magnesium plus hydrogen chloride. We have magnesium plus hydrogen chloride. This is magnesium plus hydrogen chloride. You guys will pick this with this first. This is magnesium chloride plus this. I told you hydrogen cannot stand alone, so you have to make it 2, make it 2 here. So this is 4. Magnesium is 1, hydrogen is 2, hydrogen is 2, chlorine is 2, chlorine is 2. So that's just how to balance the chemical equation. Once you see that the number of elements at your left hand is not equal to the number of elements at your right hand, you just know that your equation is not balanced at all. Okay. 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 Let me just choose one more. One more thing. You've been given a chemical formula CH2O. You've been given a formula CH2O. And then they now ask you what's the empirical formula of this compound. Now this is actually an alcohol. Now they say what is the chemical formula of this alcohol, of this compound. Now it's very, very easy to just find the empirical formula. Very, very easy. Very, 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 very easy. Now They will give you different percentages. They will give you, say, carbon is 75%. Let me see, oxygen is 15%. Just giving an instance, and hydrogen is just 1%. Now, in finding an empirical formula, there are different laws. Now, once you're being given like this, the first thing is to assume this percentage. You assume percentages, percentages in grams. Assume them in grams. So then, it now be that your carbon is equal to 75 grams, your oxygen is equal to 15 grams, and your hydrogen is equal to 1 gram. Very good. Now, after assuming these percentages are in grams, the next thing, we begin to divide each of these elements and their grams by their relative molecular number, meaning their molecular number. Molecular number. So this implies that you begin to divide this, so this is now 75 over 12, the oxygen 15 over 16, your hydrogen 1 over 1. Very, very, very simple. Okay, let's assume we're dividing this. This is 75. We're dividing 75 by 12, and you know that 12 times 6, I think this will give you 72 then. So this is 6, this is 72, 5 minus 2, this is 3. Then you now add your 0 here. You're having like 6 points. Let me say this is 6.2 something. So let me know assume this is 6.2, and then you're having 15 over 16. This is 15 divided by 16. And that's 16, 15. Okay, so now this will give you a 0 point and you're adding 150 here. So now this is more like 16 times 8. So this is 8, 4, this is 12. 1, 2, 8, this is 8, 4, 3, 4, 1, 4, 4. Okay, so this is 9, 0.9. So 0, this is 0.9, this is 144, you have 6, this is 0, 0. So you have 60 here. So let me just assume that this is still 1. So this is 0.9. So let me assume this is still 1. 1 divided by 1 is still 1. So now the next thing you have to do now is divide each by the lowest. By the lowest. Divide each term by the lowest. So now the lowest here is 1. So now divide this by 1, divide this by 1, divide this by 1. So you're still getting. So let us approximate it to 6. Then you have 1, you have 1. So remember that the formula they gave you was just. So now you have 6, 1, 1. They gave you carbon, oxygen, hydrogen. So this is how you just fix it. Although this kind of thing has never happened before, where I have C6H0. But just an example. Now your carbon finally has 6. The oxygen is now 1. And this is now 1. So this is your empirical formula. This is your empirical formula. To cover the empirical formula is very, very easy to find. So this is your empirical formula. Very, very, very easy to find. Remember the first thing I said, assume these percentages are in grams. 75% is in gram, 50% is in gram, the 1% here is in gram. I said the next thing, you divide each element by their molecular number. Divide each, 75 by 12, 15 by 16, 1 over 1. Now, the next one, I say divide each by the lowest number. by the lowest terms by 0.9. By 0.9. But because 0.9 is smaller than 5 by 1, 5 by 1, then you're getting 6, carbon is 6, this one is still 1, this one is still 1, and that's why we just break formula now, C6H2. This is your empirical formula. Empirical formula is different from molecular formula. Very, very different from molecular formula. Very, very different. You can have something like that, they will give you, let me see, so what the molecular formula, have the empirical formula of this. Now, that's C6H2. Then you find your molecular formula, you have to go into this M. Now, they will give you a little level formula of the compound. Assuming they gave you that this your molecular formula is this, and they're having a, let me see, a number of, let me see, 84. Find the molecular formula. Now this is what it tells you. You box this times n equal to 84. Equal to 84. Now you need to open this the way you calculate your little molecular number. Remember that this is C is 12, having 12 molecular number. So if you become 12 times 8, everything is 1. Everything is 1. This is 12. All these are equal. Very, very easy. So this is 72 plus 17 all n equals 84. So you now add this to stuff. You now be having 50. So you have the value of A here is what you will now use, and then you'll be able to get the molecular formula. Now let me add that the value of N here is now 7. So your new molecular formula. Your new molecular formula will be, remember that this is C6H2. Now your value of your N now is now 7. So now it's now be times 7. So your molecular formula now be 6 times 7, which is now 6 times 7 plus 2 H. So this is your new molecular formula. So now this is your molecular formula, this is your empirical formula. See, they are very, very, very different. Very, very, very different. Very different. Now I've taught you the steps in getting your empirical formula. I want to show you the steps in getting your molecular formula. Let's see one new example this time around on how to calculate it. Let's go through one major example of how to calculate it. Okay. Okay. Now they said if a relative molecular formula is this CH2O equals 60. Now then if your relative molecular formula is 60, relative molecular formula. Relative molecular mass rather. Relative molecular mass of this stuff is 60. Now they now say find the empirical formula, given that C is 12 and H is 1. C is 12, H is 1. Now how do you able to do this? Now this is quite different from just finding your empirical formula. And they say find the empirical formula. Empirical formula. Then now to find the empirical formula. Now this is quite different. Remember when I was treating, I was saying once you have an empirical formula like this, it will be N equal to your mass, your relative mass. Now, if finding your empirical formula this time around, it's going to be twice. It's going to be actually twice. going to actually try with CH2O. Okay, going to actually give me twice of your relative molecular mass. So if the molecular formula is this and the mass is equal to 60. So you now have CH2 divided by N equal to 60. Now they say your carbon is 12. Remember I said they say carbon is 12, hydrogen is 1 times 1 plus 16 times 1. So N is here, all equal to 60. Here this is 2, so N is equal to 2. Now, all you need to do now, remember this is your N. So you just come here. This is 2 H4 O2. Got the answer. Very easy. C2H4O2. And that is a very simple way of finding it once you bring in the relative molecular mass. Okay. Let me see another. Okay. Another example that we can actually go through. Another example that we can actually go through so that we're able to familiarize ourselves and then know how to get this empirical formula. To get this empirical formula. Now, mind you, they said what's empirical? I feel it's empirical. So the empirical formula here is 2. Number of this here is 2. This is the empirical formula. Okay, they said very good. I think a very good question that will just clear our minds on something. Now, assuming you're being given X, ammonia, plus Y, okay, and your product is Z, okay? Okay, so let me do that. Okay, so now we have been asked to find what this alphabet represents. Now we find X, Y, and Z. Now, more they are telling you to balance this equation. So you write it without putting those alphabets. This is NH3 plus oxygen, and then I'll give you NO plus water. Remember, when you look at whether the elements here are the same with the element at your left hand. Maybe at right hand the same with the element at the left hand. Now look here, we have one atom of nitrogen, one atom of hydrogen. 3 moles of hydrogen, just 2 here. 2 moles of oxygen, 2 moles of oxygen. Now discover that your hydrogen is not complete. Your hydrogen is not complete. Okay, let's put 2 here. If we put 2 here, the hydrogen is now 6 here. You now put 3 here. The hydrogen is now 6. Now your nitrogen has changed. The nitrogen is now 2. The nitrogen is now 2. The oxygen is 2 here, and now here your oxygen is 4. Make this like this. Very easy. Let's finish with nitrogen first. Very easy. And then you now come here. You put your 2. Really. The oxygen has now changed. This is 3. This is 5. The oxygen has now finally changed. So I discovered that we are now making a mistake here. You cannot just make it. Nitrogen is 2, hydrogen is 6, hydrogen is 6, nitrogen is 2. But now your oxygen is 2, and your oxygen here is now becoming 5. Now because this equation is not balanced, we go back and then look for how to balance the equation to make sure that your oxygen, the number of electrons, the number of atoms in the oxygen should be equal to 4. atoms here. So you look carefully to what's missing really out. It is your chemical equation. Okay. So now what if we have what if we have 4 here? What if we have 4 here? So that means we have 4 here. Here will not become 8. What if we have 4 here and here is 12? We have 6 here, making it 12. So that means your nitrogen here is now 4, and your oxygen here is now 10. You now have 5 here. Now let's look at it very carefully to see if it's balanced. Now your nitrogen is 4, your nitrogen is 4. Your hydrogen is 12, hydrogen is 12. Your oxygen is 10. Your oxygen is 10. So now your value of x here is 4. X is equal to 4. Your y is equal to 5. Your z, your balanced equation. See now that you are getting your balanced equation. Your x is 4, your y is 5, your z. You bring down your equation without putting the alphabet. You bring them down without putting the alphabet. Then you have x is equal to 4, y is equal to 5. I repeat, how did we actually get this? You have your ammonia plus your oxygen, giving you nitrogen oxide plus water. Now, let's go back to see how we did it. Told you your ammonia is just 1, your hydrogen is 3, here your hydrogen is just 2. Your oxygen is 2, your oxygen here is 2. The problem now we have is your hydrogen. How to balance the hydrogen? So now, in order to balance it, I said at first I use 2. Okay, your nitrogen is 2, here is 2. And when I use that, I use 3 here. So when I use that, I said, okay, your nitrogen is 6, your hydrogen is 6, your hydrogen is 6. But how about the oxygen? Now the oxygen is now scattered. And that's why I have to erase the day, because when dealing with chemical equations, you must make sure that what's at the left is equal to what's at the right. And so I decided to use 4. And I said, okay, 4 times 3 will give me 12. So my hydrogen is now 12. So 6 times 2 will give me 12. Very good. My nitrogen is 4, so my nitrogen should be 4 here. Okay? But now my oxygen here now is now 10. My oxygen is 12 hydrogen, 10 oxygen, 10 oxygen. So value of your x is 4, your q is 6. Very, very easy. As simple as that. Very, very, very easy. Okay. Okay, let's move on now with the trials on nitrate 5. Okay. Because I'm just trying to reserve other ones that will actually the various laws of chemical combination, laws of multiplication, laws of conservation, and laws of multiplication. All those ones are what we'll choose. Okay. I said, remember, I'm just mixing it together. I'm probably mixing these chemical equations and empirical formula. Because once you're able to do these chemical equations, how to form them, how to react them, how to balance it, you should not have any issue knowing your empirical formula. Now, imagine I don't give you something like this is an empirical formula. Let's say find empirical formula. Find the empirical formula. Empirical formula. Define the empirical formula. Now they gave you this nitrogen to be 26 this time around. Okay, 26.17%. 17%. They say your hydrogen is 7.4.35%. Now say calculate the empirical formula of this. Now very, very easy. Very, very easy. Remember all what I said? I said the calculated efforts, you assume the per 7 gram. Your H is 7.48 grams. Is that you divide each by their molar mass. Okay? Molecular mass, anyone. Now divide each. Now nitrogen has a molar mass of 14. Okay? Of 14. Hydrogen has a molar mass of 1. Chlorine has a molar mass of 35.5. All these are in gram per mole. The symbols are very, very important. The symbols are very, very important. The symbols are very, very important. So now, once you've been given like this, I said the next stage, after dividing each term, so you now divide this one now. This is 26.17, 5.5. Okay? So now let's see how we are going to divide them carefully. Let's see how we are going to divide it carefully. Okay, this time around, I think we'll be using our calculator. Then we will divide this. Now, the nitrogen is equal to 26.17 over 14. So once you just divide 26.17 divided by 14, you are having 1.87. Then your hydrogen, then your chlorine. Your chlorine now is now 66.35 divided by 35.5. So that's 63.35 over 35.5. 35.5. Okay? So now to give you the same 1.87. So now I told you the next step is to divide by the lowest number. Divide each by the lowest number. By the lowest number. So the lowest number here is 1.87. So we get 1.87 over 1.87. 7.48. 7.48 divided by 1.87 will give you 4. 1.87 divided by 1.87 will give you 1. Chloride. Very, very easy. Very, very, very easy to understand. So this is ammonium chloride. Let's still go through 2 more before we end up today. Let's go through 2 more. Let's go through 2 more questions. Then we'll round up. 2 more questions. Okay. Now, being given calcium to be 71.43. Now your calcium is 71.43%. Then your oxygen is 28.57. I said you first assume the percentage to be in grams. Assume your percentage to be in grams. So that means you are having 71.43 gram calcium. Then your oxygen, which is 8.57 grams. Next, I said we divide each by term is 40. Having a molar mass of 40, you should be able to get all this in your head. And then your oxygen is 8.1.48 divided by 40. So I get 1.787. Something like that. You're having 28.6% divided by, what will just give you 8.57 divided by 16. So you have a 1.7, let me see, 786 this time around. So now the next I say divide by the lowest. I say divide each by the lowest number. By the lowest number. Now this 1.787, 1.786 is smaller than 1.787. So 1.786, 1.786, 1.786. So this is 1. Then 1.787 or 1.786. This is also one appropriate. So now discover that your calcium is 1, your oxygen is 1. So what you get is this CaO, calcium oxide. Calcium oxide, also known as quicklime. Known as quicklime. So this is calcium oxide. This is your empirical formula. This is your empirical formula. This is your empirical formula. Okay. Let's go one more. Let's go one more. Let's go one more. Okay. It said this time around I gave you silver, nitrogen, and oxygen. We use silver as this of Ag and metal. So they say silver 63.53 is 63.53%, 8.23%. Then I gave you sulfur. Okay, let me use oxygen to 8.24. Don't get tired of using the same processes. You assume that each is in gram. So this is 63.53 gram, 8.23 gram. This is 28.24 gram. Very, very, very easy. Okay. So now I said divide it by the molar mass. Silver here have a molar mass of 108 gram per mole. So now we now dividing each. So this is going to be 63.53 over 108, 8.23 over 14, because that's the molar mass of nitrogen. Then 28.24 all over 16 molar mass of oxygen. Okay, so we divided 63.53 over 108. We're getting 0.588. Now you're dividing 8.23 by 14. You're getting 0.588 also. Then you now divide 28.24 divided by 16. What you'll be getting here is 1.76. 1.765. Okay. Now the next step I said you have to divide it by the smallest amount, by the lowest amount. Now the lowest amount among these is 0.588. So now you divide each them by 0.588 over 0.588 over 0. So that means your silver here, your nitrogen is 1, the nitrogen is 1, the oxygen is 1. So you need to break the formula to now be this one. This is your Ag. So See what else you like it. Now this is the new empirical formula. Empirical. The new empirical formula. Okay. Okay, there are other ones that. Okay, let's just do this last one. Let's just do one more. Let's just do one, just one more. Just one more. One more question here. They said your sodium is 32.40%, oxygen is 45.0. So that's why you're dealing with sodium. You're dealing with sodium. Sodium 32.40. Sodium 32.40%. Oxygen 45.22.53. The sulfur 22.53. I said assume your percentages to be in bars. And we have it 32.40 grams. You'll be having your oxygen to be 45.07 grams. Your sulfur 22.53 grams. As easy as that. Okay? So the next thing here now, I said divide each by your molecular mass or your molar mass. Sodium has a molar mass of 23. Sodium has a molar mass of 23 grams per mole. So now you'll be dividing 32.40 over 23. That's your sodium. For your oxygen, remember oxygen has a molar mass of 16, so to be 45.07 over 16. And your sulfur has a molar mass of 32 grams per mole. So we're dividing 22.51. Let me just do 1.41. Then you're dividing 45.07 divided by 16, we get 2.82. Then you divide the next one to 2.53 divided by 32. Now we're getting 0.70. Now the next one I said you divide by the smallest amount. 0.7 is smaller than the rest. So divide each by 0.70, 0.70, 0.70. So that will be 1.41 divided by 0.70. Now this will give you 2. So just gets 2. You divide 2.82. 2.82 divided by 0.70. We're getting 4. So your oxygen is 4. Divide this, we're getting 1. Now, what you now be getting is just this. Now getting Na2 SO4. So temperature of sulfate 6. Very, very, very easy. Very, very, very easy. Na2 SO4. The sodium after the calculation is 2. Your oxygen after the calculation is 4. And your sulfur at the end of the calculation is 1. So another thing is being able to rearrange them. The sodium, your sulfur, and your oxygen. Now, to name this compound, this is sodium tetra. Why is the root of the X plus bracket your 4 axis has minus 2 at this side. So you have 4 times minus 2, all equal to 2 minus 8 equal to 0. So x 2 minus 8 will give you this is minus 6 equal to 0. So this implies that the x is equal to 6. So this implies that the sodium tetra also sulfate 6. Also sulfate 6. That's how you actually get it. Sodium tetra into sulfate. This is your equation. This is your equation formula. This is your equation formula. Very, very, very easy to understand. Very, very easy to comprehend. Very easy to understand. Very easy to comprehend. Okay. Okay. We're going to be dealing with one more thing about these chemical equations and the rest. Now, assuming you will now give me a question, how many moles are found in this equation? How many moles are found in this equation? Now, you've been given a chemical equation. You have hydrogen, H2, you have hydrogen H2, okay, plus oxygen, and it's reacted and give you water. You all know that give you water. Very, very easy. Now, they now ask you to calculate the number of moles of oxygen. Calculate the number of moles of oxygen required to yield 6 moles of water. Calculate how many moles of oxygen required. Now, this equation is not actually balanced, so you have to balance it. So this is 2, the equation is now balanced. So now they're asking you to calculate the number of moles of oxygen required to yield 6 moles of water. Now, if you look so carefully, 2 moles of oxygen here, 2 moles of oxygen here, they are going to how many moles of oxygen can yield 6 moles. So now, 2 moles of oxygen here, 2 moles of oxygen, 2 moles of oxygen here, or rather 1 mole of oxygen, because it's just 1 mole of oxygen gives you 2 moles of water. 1 mole of oxygen here gives you 2 moles of water. Now they're asking you how many moles of oxygen will give you. So let me just say X mole of oxygen that should give you 6 moles of water. Now this is just a normal cross multiplication stuff. Now this now be your 2x is equal to 6 has 3 moles of water of oxygen. 3 moles of oxygen to get 6 moles of water. How do you actually write that chemically or in the chemical equation? Just copy it. Yeah, so you put your 3 moles to give you 6 moles of water. So that means what to be is also 6. As easy as that. Very, very, very easy. Very, very, very easy. That's just how to find the moles here. 3 moles of oxygen needs 6 moles of water. Now, that's what I said. Sodium combines with oxygen as follows. Sodium plus oxygen. Sodium plus oxygen to give you. Now you have sodium plus oxygen. Sodium plus oxygen to give you the sodium oxide. So you have this sodium oxide. You have 4 atoms there. You have 2 atoms here. Okay, very good. Now the question is, what's the mass of oxygen needed to burn 4.6 grams of sodium? Now they ask you what's the mass of oxygen needed to burn 4.6 grams. Now from the reaction, you have 4 moles of sodium. 4 moles of sodium was able to give you 1 mole of oxygen. What is the mass of oxygen needed to burn 4.6 grams of sodium. Now the next thing now is how to get mass of sodium to be equal to 4 times 23. Remember that the molar mass of sodium is 23. So we got 4 times 23. Now 4 times 23 will give you 92 grams. Giving you 92 grams. If a mass of 4 moles of sodium is 4 times 3, which give you 92 grams, then a mass of 1 mole equal to, remember this oxygen is more like 16 times 2 because of this 2 here. So you now get 16 times 2, which will now be something as 32 grams. Now, since 92 grams, now we are finally converted from moles to mass. Since we are being asked a question, what is the mass of oxygen? Now we burn 4.6 grams of sodium. So now it's of oxygen. 32 grams of oxygen. Now they are asking for give us X gram of oxygen. To give us X gram of oxygen. So now, like we did again, you do what? Cross multiply. So now you now be having 4.6 times 32 is equal to 92 times X. Now once you multiply 4.6 times 32 to give you 147. 147.2 is equal to 92x. You divide both sides by 92. Divide both sides by 92. So what you're now getting 1.47.2 divided by 92. Now what you'll be getting here is 1.6. So this implies that it requires 1.6 mass of oxygen to burn 4.6 grams of sodium. So therefore 1.6 grams of oxygen burns 4.6 grams of sodium. Very easy. Very easy. Now it depends on the question they give you. If they give you the question a mole, to find it a mole, there's no need of converting to mass. But if they give you a question in moles and they say find it, be able to burn 4.6 grams of sodium. So now, from the question here, 4 moles of sodium is more related with 1 mole of oxygen. Now, to convert these 4 moles to gram, you multiply the 4 by the molar mass of sodium, which is 2 here, so it will be 60 times 2. Now, assuming there was a 2 here for the sodium, you'll be having 4 times 23 times 2. But since there's no 2, that's why we just have 4 times 23 equals to 92. And then 60 times 2 equals to 32. So this implies now that 92 grams, instead of 4 moles of sodium, now you have 92 grams of sodium gives you 32 grams of oxygen. Then 4.6 grams of sodium gives you X grams of oxygen. Since you are looking for a number of grams of oxygen that can give us 4.6. Now you cross multiply. 32 grams of oxygen multiplied by 4.6 grams of sodium, 92 grams of sodium multiplied by X grams of oxygen. And when you multiply, you get 147.2 equals 92x. Now divide both sides by x, that'll get your value of x. 92, this goes out. This strikes themselves out. Now you're left with 147.2 divided by 2. So answer here is 1.6. So this means that 1.6 grams of oxygen burns 4.6 grams of sodium. Just one more and then we'll be able to round up for today. Just one more question. Okay. There's a question, hydrogen molecule. Now, when you hear that one, how many atoms are Now begin to remember Avogadro's law. How many atoms are contained in one mole of hydrogen molecule? Now, once you start here, Avogadro's law, a mole is equal to 6.02 times 10 to the power 23. 1 mole equals 6.023 times 10 to the power of 23. That's Avogadro. 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 Time again, and I just hope that you continue going through what we have already done. And I please plead that if you are pressed in any form, you can just